Hey, Mitch.
Hey, if you don't mind, we have that trip to the waterfall coming up. There's a 10 dig for point A and a 10 dig for point B. I need you to get a route from one to the other. Just make sure you avoid all the drainages. That'd be great.
Sure.
For point A, 10 dig,
I'm done.
Most of us, myself included, will use a GPS on whatever device in order to direct us to our final destination. Now, GPSs are great, don't get me wrong. It is a great tool. However, batteries die, signals and satellites, they can still fail, and the majority of people who have never needed to use a paper map before, well, those of us who remember using road atlases, they may have forgotten a few things here as well. So we wanted to provide to you the basic starting point for map reading. We're going to be covering a lot of the different types of maps and charts. We're also going to be going over the layout of a map with all of its features and the marginal information, how to identify what system is being utilized on that map, as well as how to plot and read coordinates for each of those systems. Now, again, this is just the beginning of the rest of the series. We'll also be bringing you guys a lot more content on how to utilize all that information for land navigation and route planning and all that sort of stuff later on. But it's important to know the basics first before you start getting into that stuff. So, the basics. Maps and charts. What's the difference? Well, maps are used for covering a small amount of the Earth's surface by land, whereas a chart is used for navigating large portions of the Earth by air or sea. You also have some that are like geological charts, but who cares about those? Now, they differ mostly inside of the scale, but also in how some of the information is being represented. Now, regardless of the type, your map or chart, you'll have a legend. Now, the legend provides all of the information that you need in order to properly interpret the map or the chart. Now, the legend defines all of the symbols and the different colors. It provides you with the scale of the map, which is just the relative ratio to what's on paper to what it is around you. It also has the map datum, which is used in order to place the grid on the map with the geospatial imagery. A declination diagram should also be present. This is also known as a compass rose or a northing arrow, whatever they want to be calling it. It's what shows you north. Now, they should also have a date. All of these are vital for accurate navigation, but most importantly is the date. Things change, and although old maps are cool and all, they don't possess accurate information for precise navigation. The topography of an environment isn't the only thing that changes. Over time, we see that the magnetic pull from north also does, which is why we have a declination diagram to begin with. It tells you that at the time that map was created, the Earth's magnetic field was pulling a compass off of true north by this exact amount. And it's changing every single year. So make sure that your maps are up to date and you know the accurate information, otherwise you could be going in a completely wrong direction. Now, having a scale representation of an area is awesome, but it doesn't do you any good unless you can actually provide the exact description of a location, like a global address on that map, which is where we get into the three different most popular mapping systems utilized out there. Now, the first of them is going to be one of the most recognized globally, and that's latitude and longitude. Lat and long provide a grid system used to pinpoint any location on the planet. Hell, We even have lat-long coordinates set up for Mars already. Now, latitudinal lines, also known as parallels, run horizontally, starting at the Earth's equator. They also, at that point, it's what also provides us the northern and southern hemisphere. North above the equator, south below the equator. There you go. Now, latitude measures the distance between the equator at 0 degrees all the way up to 90 degrees at the poles. This can be written in a few different ways. You can have your hemisphere, which is going to be indicated by simple shorthand, N for north, S for south, or you could have a positive 2-digit number strain for your northern hemisphere and or a negative 2-digit number strain for your southern hemisphere. Now, longitudinal lines, also known as meridians, run vertically from the pole to measure the distance east and west of the prime meridian, which is right there. Prime meridian is 0 degrees, which also happens to be the start of the global time zones, or GMT, which is Greenwich Mean Time, and it continues to 180 degrees at the reverse meridian, aka the international dateline, which is also gives us our eastern and western hemispheres. Go figure, if you're east of GMT, you're in the eastern hemisphere. If you're west of GMT, you're in the western hemisphere. Yay! Now, the eastern and western hemispheres can also be divided into 2 different ways, whether it be simply an E for east or a W for west, or you could also have a 3-digit number for your eastern hemisphere or a negative 3-digit number for your western hemisphere. Now, when we're reading latitude and longitudinal coordinates together, latitude is always the first set, followed by the longitude. For example, the coordinates 40 degrees north by 0 to 0 degrees east, or 20 degrees east, represents the location 40 degrees north of the equator and 20 degrees east of the prime meridian. This can also be seen as 40 degrees break 0 to 0 degrees. Now, notice that even though the longitudinal coordinates don't fill all 3, we put all 3 of the digits inside of the longitude. This is to indicate that they are meant for longitudinal coordinates and not to be mistaken for latitude. In the case of a broken transmission, we want to be able to make sure that the recipient may not inadvertently receive the second set of numbers before the first. That's why we make sure that our latitude has 2 digits for degrees and our longitude has 3 digits for the degrees. Now, a 1 degree box by a 1 degree box is still a very, very large area. So we can further refine to an exact point in 2 different ways. The first is going to be using a decimal system. Now, it's going to be decimals of the degree. All that is subdivisions further through the decimals, just like factors of 10. So if we were going to this set of coordinates, like so, you can see that's really broken down into a further point, right? Now, another way is also by using minutes and seconds. Now, when we're dealing with it as minutes and seconds, we treat each degree as the value of 1 hour. And as such, each degree contains 60 minutes. Also, each minute contains 60 seconds. So those exact same coordinates right here, if we were going to translate that from decimals into minutes and seconds, it would look just like this. Same, but different, but still same. Now, the next system is the Universal Transverse Mercator system, or UTM for short. Now, unlike latitude and longitude, which uses a spherical coordinating system, UTM employs a flat rectangular grid. Now, like latitude and longitude, UTM is a horizontal positioning representation. Big words, all it really means is that both of those systems ignore altitude and treat the Earth's surface as if it were a perfect ellipsoid. UTM divides the Earth up into 60 different zones, and it projects them to form the perspective of the zone's central meridian, or where its central longitudinal line intersects the equator. Now the zones range from 1 starting at 180 degrees west, or the reverse meridian, so it's kind of the opposite of latitude and longitude, and it increases in values from east, or moving towards the east. We also call this easting. Now each of the 60 zones are equal, save for an exception in Northern Europe, given off for some grid zones in 31N to 37N. It gets all kind of wonky. They just kind of cross borders a little bit, and it's not even divided. I don't know why they did it, but they did it. Now, latitudinal limits for UTM is going to be 84 degrees north and 80 degrees south. So we cut off the top and the bottom of the globe as we roll it out into a flat sheet. Yes, some of the zones overlap, but just due to the fact that it is a flat interpretation of each 60-degree meridian of the sphere. Now, UTM always reads from left to right, and then from bottom up. To avoid dealing with negative numbers, a false easting of negative 500,000 meters is added to the central meridian. So whichever zone you're in, the central meridian, or that actual longitudinal line that's on there, is going to be 500,000 meters to the center, which means that you'll also have 500,000 meters to the east and 500,000 meters to the west. So your easting of, say, 400,000 meters on that UTM system would actually put you 100,000 meters west of the central meridian for that zone. Now, northern coordinates start with 0 meters at the equator and get up to 9,300,000 meters at its latitudinal limit of that 84 degrees north. Now, this is also known as the 84th parallel. Just know above and below the UTM range, it has its own system. Now, because northern always increases in value with UTM, going towards the north, the farthest south UTM goes to is 1,100,000 meters, starting at that 80 degrees south latitude and then working its way up to that 10 million at the equator. Now, both above 84 degrees north and below 80 degrees south, they have their own unique UTM zones for mapping the systems and everything else like that. So, unless you're going to the North Pole or Antarctica, you'll learn about it then. Now, UTM coordinates are represented as a pair of values that follow this pattern. Left to right, or your eastern, followed by bottom up, which is going to be your northern. Now, being a Mercator or metric system, all the values of UTM are expressed in meters. So your values will see pretty long and lengthy, but it will look something like this. It'll be followed by your zone, easting, and then northing. For example, this shows a location that is inside zone 33 at the center of the longitudinal meridian, which, remember, is going to be that 500,000 meters east of the edge. Cool. And 4,400,000 meters north of the equator. Because, that's right, it's going to be above that 9 million start off point. Now, UTM uses a lot of numbers that can get very confusing due to the scale of the zones being utilized, which is why the military grid reference system cleans that up by providing more starting reference points, but makes the information easier to process. You don't have to count as many placement values. Now, MGRS provides a precise way to communicate locations on the Earth's surface with a varying degree of accuracy. It combines elements of latitude and longitude with the tools of UTM in order to produce an alphanumeric coordinate system that has gridded sections for each part of the planet. MGRS is also read from left to right, and from bottom up, just like UTM. But It divides the world up into grids of 6 degrees longitude by 8 degrees latitude. Each of these grids has its own number letter identifier. The letters range from C to X, excluding I and O. Now, why does it eliminate I and O? Well, it's simply to avoid confusion, because when you look at the letters I and O, depending on the font, they look very, very close, almost the same as 1 and 0. So now we have the same 60-degree latitudinal bands as the meridians that are utilized in UTM, but they are each divided into 20 different sections, giving us 120 number letter combinations that the globe is now broken up into. But what about A, B, Y, and C? Like you said that it starts at C, then goes on. Yeah, we know. That's because A and B is utilized for the UPS, or the Universal Polar Stereographic. Yeah, mouthful. And Y and Z are used for the North Pole. So the UPS system is the South Pole, that's Antarctica. You can go look it up. It's a pretty crazy map system that they have. And then Y and Z, North Pole section of the globe as well. Now, each of the 6 by 8 degree grids is further subdivided into 100,000 meter grid squares. Each are assigned by a 2-letter combination. The first represents the column and the second represents the row. The letters for the 100,000 meter box range from A to Z for the columns and A to V for the rows. Now again, this is omitting the letters I and O, again, just to prevent confusion. And the letters increase alphabetically from west to east and south to north. All right, now within each one of those 100,000 meter grid squares, locations are further specified using easting and northern coordinates, just like UTM. Your easting measures the distance eastward from the western edge of the grid square in meters, and northern measuring distance northward from the southern edge of that grid square in meters. Now, both easting and northern coordinates are expressed as a numerical value with the same amount of digits. It's important that they're the same. The number of digits used to express the easting and northern coordinates determines the precision of the MGRS coordinate. For example, a 1 meter precision grid box set of coordinates is expressed as a 10-digit set. So you'll have 5 for your easting and 5 for your northern. While at a 10 meter precision coordinate box, so within 10 meters, it will use 8 digits, 4 for your easting and 4 for your northern. Following on, 100 meter precision or within a 100 meter box is going to be a 6-digit set of coordinates, 3 for your easting, 3 for your northern. Now, fully written out MGRS coordinates will look something kind of like this. You got your number letter grid zone, followed by your 100,000 meter letter grid, and then your easting, and then your northern. Now, once you know the grid you're using, the number letter and letter usually ends up getting discarded. Everybody knows that you're within this giant frickin' area, and you're working simply with just the digits in order to find somebody's actual location. Now, you may just hear people ask for an easting and northern at that point, also known as their dig. And the value of that dig determines how accurate they want you to be with your coordinates. Again, this is just an intro into understanding the maps, but we will be making a whole other video on how to use them for further into land nav, building checklists, everything else like that, shooting azimuths, compass work. Everything's going to be coming up later. We just wanted to give this first initial taste to you guys right off the bat. Now, if you're needing to brush up on your map reading and plotting skills, we're going to have some free downloadable content on our website. Link's going to be down below with worksheets that we've created for you to practice reading and plotting coordinates. It's also going to come with a master key in order to help you verify some of your work. So go ahead, check that out, and get some practice in before you actually need to utilize it.